I mentioned that palladium-catalyzed carbon-carbon bond coupling reactions are really, really important in modern synthetic chemistry. You really can't make anything without using organometallic catalysts at some point, and usually palladium. So we've focused on the Suzuki reaction here, but there are other equivalents with other kinds of atoms that we won't get to talk about much in this class. So for instance, if I had alkyl tin compounds, the Stille reaction is very useful. Alkyl silicon compounds, we can talk about the Hiyama, zinc, Negishi, magnesium, Kumada, and there are others. And so we don't need to go into all those different reactions. They all basically keep the same catalytic cycle and same utility as a Suzuki reaction. But of all these, people like the Suzuki the best because it works the best. Maybe the Stille works a little bit better, but it's harder to get tin compounds, and tin compounds are very toxic. And so in terms of cost, effectiveness, the lack of toxicity, the Suzuki really stands alone as being special among all of these. One other reaction that is really special and really widely used isn't in your textbook, but I still want to talk about it. That's the Sonogashira reaction. So the Sonogashira reaction is the best way to make a new bond between an sp2 center and an sp alkyne center. And the other nice thing about it is that I don't need to start off with a fancy organoboron or organotin or whatever. I can just start with an alkyne, a normal terminal alkyne, so an alkyne with the CH on the end, and again, some sp2 carbon with a leaving group, chlorine, bromine, or iodine. I'm going to need two catalysts for this. So I need both a palladium catalyst and I need a copper-1 catalyst. So copper iodide is a good example. Throw in some base, and this will very effectively and in high yield give me a new alkyne carbon bond. I won't go through the full catalytic mechanism of the Sonogashira reaction. It's pretty complex and people are still doing research to nail down some intricacies in the mechanism. But the way I think about it is this. So my alkyne reacts with the copper species and the base to give me actually a copper acetylide. So I can think of this as almost a little bit similar to our Gilman reagents, where I've got a copper carbon bond. That copper carbon species, and copper is especially good at making bonds to triple bonds like this, that's going to transmetallate or change partners with this palladium species that I get from oxidative insertion into that aryl X bond. So these two are going to change partners. The copper is going to end up with both leaving groups, like copper Br2 or something like that. And palladium is going to end up with both carbon, two palladium carbon bonds, which after that palladium wiggles out and re-enters the catalytic cycle, I get this new product by reductive elimination. This is all about pattern matching. Anytime I see a new, if I need to make a bond between an alkyne and some sp2 carbon, I'm going to think about trying to use the Sonogashira reaction to do so.